kind of a subcategory of corrosion is a macrobiological corrosion, and macrobiological corrosion means, the word macro means you can see with your eyes. I think they have not yet fixed the pointer. It moves in a different direction. So I'll use the laser pointer instead. So the word macro here means you can see with unaided eyes, and biological means when it is affected by the biological organisms. So some organisms which we can see with our eyes are, for example, the first case is fungus and molds. Now they can be classified as the plants that lack chlorophyll, or some people classify them not in the plants at all. Whatever it is, they are the living organisms, and when they come and deposit and make colonies over the surface, because of the biological activity, they can create organic acids. You can look at the screen on your left hand side when I'm using the pointer, and they can grow on the leather and rubber things, and once they make the deposit, so the corrosion that is triggered because of the deposit, if you recall, is the crevice corrosion. So they can create the situation for crevice corrosion, and they can fade the look of your component on which they are making the colonies. So it's only the surface damage that they can create, and the mechanical damage is not significant. But nevertheless, you don't want that kind of deposits to be even made. So the best way to minimize this kind of corrosion because of the fungus and molds is that you have to clean it, because once you clean it, you eliminate it. Number two, you can reduce the relative humidity. Can you tell that why the reduction in the humidity will try to minimize the macrobiological corrosion by fungus and molds? Why the humidity is very important? So on the same line, I can ask you a question, for example, that will the microbiological corrosion by fungus and molds will be more prevalent in the open atmospheric condition or in the air conditioned room? That's an outshoot question. So can anyone think that why the humidity is important? And if we kill the humidity, we can kill this kind of corrosion. All the living organism needs water to survive. You deprive them of the water, they will die themselves. That's the reason. You can poison them. Any living organism can be poisoned and killed. So in this case, gentian violet is the one which is used, and you can use a synthetic rather than natural rubber. So rubber is used in many engineering applications. So try to go for synthetic rubbers where they don't allow, or this organism cannot take the nutrition out of this the synthetic rubber. Now we also have seen macrobiological corrosion because of the red ants, and if you look at this situation in 2015, the brake pad fails in the train, and apparently the driver has to use the manual brakes to stop the train because the red ants infested and ate the cables. So they first ate the protective coating, and then they ate the cable, and as a result the whole system went down and the people have to use the manual brake. So this is another example of corrosion because of the living organism, something which you can see with your eyes. Another case which I heard of is the rats. Wherever there are power transmission lines, and at the bottom of it they protect the lines by rubber encasing and all this thing. So this rat comes in the night and chew away all the protective coatings, exposing the metallic surface outside, leading to the corrosion. So there are many cases of macrobiological corrosion. Then we have microbiological corrosion. The biological organism that we cannot see with our unaided eye. So you need a microscope or magnifying lens or maybe some other kind of magnification procedures to see these organisms. Bacteria are the example. You can have two types of bacteria, aerobic and anaerobic. Aerobic are the one which needs oxygen to survive. Anaerobic are the one which does not need oxygen to survive. Now, irrespective of the fact that whether they are aerobic bacteria or anaerobic bacteria, wherever they come and settle down, they will be involved in some kind of biological activity. And whenever they are involved in the biological activity, it will create a corrosive environment. And because of the corrosive environment, the place where they are making colonies, you can change the concentration of the solution. Or you can have a one type of solution at one end where they are making colonies and a natural environment at the other parts. So once you have this cell form now, because of the different environment, you can have an anode and a cathode. Number 3, they can also damage the protective film on the metal. And because of these 3 reasons, A, B, and C, or the first 3 reasons, they can influence the anodic and cathodic reactions. And once they do that, then your corrosion starts. And then it will continue on. This was first seen in London or highlighted. I'm sure the people might have seen it in many places, but this was highlighted and glamorized to the international media when the sulfate-reducing bacteria ate away almost 100 meters of cast iron tunnel near Moorgate station in London. That's a tons of material gone. The tunnel was totally destroyed. And same thing, it is not only iron-based material. If you look at this picture, you can see all these pits are formed, and that is where the bacteria made colonies. So they ate away this metal. And in this case, it's a fuel tank made of aluminum alloy. So they can be mitigated. Their action can be mitigated. You can use the bituminous coating or you can use the cathodic protection. So there are ways to mitigate it. Now here are some photos which shows that inside the pipelines they can make colonies and they can keep building up on the colonies and they can reduce the inside dimension of the pipe, leading it to become more difficult for the liquid to pass. And in the meantime, they can also damage the surface, which I'm going to show in the next few pictures. Now here is an outcome of what happens when these microbiological, especially the sulfate-reducing bacteria, there are other families also, if you don't check them, if you don't control them in the pipes. Now, this is a pipeline rupture in New Mexico, August 2000, not very far behind in the history. It was a 30-inch diameter pipe carrying natural gas near to the New Mexico, and it blew up. 12 people died, 3 vehicles damaged, and including 2 suspension bridges. And you can see the big crater form where the explosion took place. It was made of steel. Most of the pipes are made of steel. And the last inspection was only 1 day back, and there's no evidence of signs of leakage. Because when the oil or gas will leak, it will try to make the soil wet, some kind of colorless thing, and it can poison the environment, so the vegetation will die. So there are some telltale signs if the leakage is happening over time. So it was not happening. The pipe was never inspected, not pressure tested, and that was the biggest mistake made. And apparently when they analyzed it, they saw the presence of pits on the surface of the pipe, and a high magnification picture shows you that these pits are going deep and compromising on the thickness of the pipe. So basically, when the effective thickness of the pipe is reduced, no matter at what location, and when you pass these liquids or gases, you have to pass them through certain pressure. So now if you compromise on the thickness, the stress in that part will increase. And when the stress increases, it blows off. And that's exactly what happened. So the operating pressure was okay. 80% which is allowed. When they did some X-ray studies, they found the presence of chlorine and sodium, and they found sulfate-reducing bacteria, acid-producing bacteria, anaerobic bacteria, and aerobic bacteria. So they found all kind of bacteria in these pipes. So what really happened is that these microbes came in with a fluid, they settled, they made colonies, and when they enter into the biological activities, because they are living organisms, they create a corrosive environment. Then they start eating on the pipe wherever they are deposited. The pits are formed, and these pits slowly grow, and then the thickness of the pipe is compromised, pressure is there, the stress concentration, and it's a over-stress failure. Remedies? The first thing is that you have to ensure that you do some kind of maintenance or inspection of the pipe from inside. Now it is followed almost worldwide. There's something which is called as a pig device, a kind of machine which you can put in the pipes, and it can go along the pipe, and it will give you very useful data about the corrosion inside the pipe. Outside you can still see, inside you cannot see. Number 3, you have to take the samples from the pipe from different locations to ensure these microbes are not growing inside. If they are growing inside, then use a method to kill them, or use certain methods to clean the pipe from inside. Now, that case study was from, again, the oil and gas industry, and here is another example why it is a serious problem in the oil and gas industry, because again, the sulfate-reducing bacteria are the one which are the main culprits, and you see here these presence of these microbes are responsible for 40% of internal pipeline corrosion. That's a very big number, 40%, almost half. Sulfate-reducing bacteria, and you can see a picture which shows this SRB, or sulfate-reducing bacteria, and when they enter into the biological activity, then you get the corrosion product like iron sulfide and EPS, which is extracellular polymeric substances. Now, picture on the top row on your which side? Left side. All right. So, if you look at this picture, this is a surface with the bacteria, a bit high mag picture showing all this SRB bacteria, and compare this with this surface which is very clean. So you don't have any bacteria here. So this is the difference. And here's the part with the bacteria. Once you clean this bacteria away, you see a lot of pits here formed. And if you look at the cross section, you see that these pits can really go inside in depth. And that is where you can almost compromise on 70% of the thickness of the pipe when you have the failure situation. So that is the importance of the microbiological corrosion. So macrobiological corrosion, the biological organism you can see with your eyes. Microbiological corrosion, something which you cannot see with your eyes. Macrobiological normally happens on the outside surfaces, but microbiological are more dangerous, and they happen inside, like inside the tank, inside the pipe, and all this thing, something which you cannot easily see. Even if it's happening outside, you cannot really see it. So that is why we have to be more careful. And many times when you lay the underground pipes, for example, or tunnels, you have to check the soil to ensure that these bacteria does not thrive there. If they thrive, then you have to either do the bituminous coating or cathodic protection to ensure that their effect is mitigated. All right? So this is in summary of macrobiological corrosion and microbiological corrosion. Any questions so far for these two type of corrosion, biology-related corrosions? No? All right. Other types of corrosion. Exfoliation corrosion is also a very important type of corrosion. It's a kind of intergranular corrosion. What happens is that when you make the metal in the foundry, you have to either forge it, roll it, or extrude it to give it a final shape. Especially when you have to use in the sheet form, then you have to roll it. But once you roll it, the grains become elongated. So if you look at the microstructure, you will see the elongated grains like that. So you have a directional structure. Now, if you are dealing with high strength alloys, the high strength comes from the second phase. So when you have a directional structure and you have a high strength alloy, then this second phase is, you can see as a dots here, the black dots, they tend to precipitate at the grain boundaries. But the grain boundary are the defect zones, so they want to precipitate there. Now once you have a precipitate at the grain boundary and you have the inside of the grain, which is white, and a precipitate here, so they make galvanic cells. And when they make galvanic cell, so if it is exposed to the wet environment, the corrosion starts. And the corrosion starts near to all these black dots here, because they are the ones who are making galvanic cell with the surrounding matrix, which is in dominance. So the corrosion takes place along the grain boundaries, which are long now. And when that happens, the grain after grain start coming out. We call that as leafing in form of leaf. So it's a high aspect ratio, flat grains keeps coming out. And at time, when the surrounding environment can penetrate inside, the corrosion product can also form along the grain boundary, and they tend to swell the metal, and the surface layer will get a bit swelled, and it can also lead to the structural failure. Now here are a few examples of the exfoliation corrosion. You can see the surface is a bit lifted up. Here even the whole part is gone, and again you see the surface are being lifted up. So these are the evidence of exfoliation corrosion. Here is another example. You can see that the top layer is being lifted off and inside is a corrosion. This is another situation when after that thing you can see some kind of places where the part of the surface has gone completely. If you clean the surface, and wherever the surface layer is gone from an area, you will see a depth there. Here is an example of exfoliation corrosion in the fuselage part of a commercial aircraft, the kind of aircraft that you travel for going to the destination. They also face this kind of exfoliation corrosion, and they are maintained accordingly. So all this thing damage is coming because of the exfoliation corrosion, because they use a sheet form, and most likely this sheet form has flat grains. So essentially the root cause of the exfoliation corrosion is the flat grains, elongated, and the presence of second phases at the grain boundaries. So if you can get rid of these flat grains, you can give a heat treatment. There is a heat treatment which is called as annealing heat treatment, and you can tailor the heat treatment to ensure that your grains are not elongated. If it is not elongated and circular, then you will minimize this problem. And if you can replace this material with not so high strength material, then you don't have this second phase here, or the second phase will be very less. So again you mitigate exfoliation corrosion. Marine corrosion. These are more specialized type of corrosion, because a lot of time people want to understand that what is marine corrosion. Marine corrosion is no different from the fundamental concepts that you have learned, except that we have to understand that when you talk of marine, you have presence of sodium chloride and you have pH of 8.1, which is a alkaline solution. It's very important for the shipping industry, for the offshore industry, and they say that its cost is about 50 to 80 billions per year. That's kind of damage. So what you see in the marine atmosphere, first is the seawater. You have the composition, almost standard composition of the seawater, 3.5% sodium chloride, pH 8.1, which makes it alkaline. And you have various zones, splash zones, near the beach side, when the waves can come and hit your structure and go back. High tide, where you can experience the high tide but not the splashes. Low tide zone and quiet seawater. So if you have a splash zone, the waves come, hit, comes back. So the material will become wet. It will take the impact of the waves, and in the daytime it can dry off also. So the corrosion rate will be high. Again, the high tide, the velocity is high, so you can again have a high rate of corrosion. Low tide is okay, relatively less, and very surprisingly, quiet seawater. Again, you can expect very high rate of corrosion, because quiet seawater means the living organism will find it easy, and we call this as fouling. When the living or the sea plants come and attach themselves to the hull portion of the ship. And this I will take a bit later. So again, you can have a high rate of corrosion of about 8 mils per year. So all these types of corrosion are commonly seen: galvanic corrosion, crevice corrosion, pitting corrosion, selective leaching, fouling, general corrosion, cavitation, microbiological corrosion, and erosion corrosion. Fouling comes, if you ask me, it comes under macrobiological corrosion, because again they are living organisms. So I will show you some pictures here which I have got from Google, and it shows the fundamentals are same, except now you have neutral alkaline solution. So your cathodic reaction is standard, oxygen plus water plus electron, and you get hydroxyl ions. You combine two metals, you have the corrosion, galvanic corrosion. You can see here, this is a part which is corroding, this is a part which is not corroding. So they are two different metals. Crevice corrosion, wherever you have crevice and you don't take care of it, you can expect crevice corrosion to take place between the spaces. Pitting corrosion, you will see the formation of pits. You can see all on the surface here. Dezincification, if you are using copper-based material, remember the zinc goes out, copper stays back, and it can penetrate up to 3 mm, so it can break away your structure because it becomes porous with time. Then you have uniform corrosion, the corrosion all over the body. If your surface protection fails, whether it's the coating or something else. Cavitation in the propeller part of the ships or boats. You can see all these blades getting damaged. Initially you have the formation of pits, and in certain areas where the attack is more severe, especially at the root of the blade, it can easily detach itself. So that's it. Cavitation corrosion. We discussed that before. You can have also the microbiological corrosion. Some people call it microbiologically induced corrosion, MIC. So don't get worried about this word MIC. It's the same thing. And where you have the sulfate reducing bacteria which can attach and start creating the pits in there. And since the seawater has a lot of sand particles and all these things, so you can also expect erosion corrosion to happen. And here comes fouling. How bad the fouling can be, because many of you would not have seen the images of that. Now here is the fouling where you have the sea organism, they attach themselves to the hull portion, barnacles, mussels, and algae. Can you see how much they can attach? And that's a lot of weight if you talk of the whole ship. So once they attach, they reduce the ship speed, increase the fuel consumption, and you know that nowadays carbon tax is being implemented by many countries, including Singapore from 2019, so you cannot afford to burn a lot of fuel. Your speed goes down, so you cannot reach the target destination in time. So a lot of problems can come. So here's the picture, barnacles, then mussels and algae. See how much they have attached themselves to the hull, and you can use a high pressure water to remove them. There must be some other ways. This is how much algae you can get in the hull portion. So whenever the ship is docked and maintained, all this thing from the bottom part of the hull is removed. And that makes the ship movement more streamlined. So, fouling. Use anti-fouling paint. It has poison. It kills the living organism, does not allow them to stick in. And lately there has been a move so that this poison should not enter the sea water beyond certain extent. Otherwise it can poison the whole sea organisms. So some kind of controls have been made. You can use the chlorine gas. You can always affect this kind of corrosion. You can also go for the material selection. Copper-based materials are generally good for fouling. If the speed is high, you can use the stainless steel, because even if there is any damage on the surface, you have good oxygen supply, it can heal itself. If you ask me, you take the steel with molybdenum, which is even better. You can use the titanium or copper-based material for the velocities less than 3 feet per second, because in this case, your steel will not be able to repair itself in case of damage. So these materials are better. So it avoids the pitting, because steel can be damaged through the pitting, because chlorine can damage the chromium oxide and lead to pitting. So you can avoid that. Here is the anti-fouling patch being put in the hull. This is a picture here. This is one of the ways in which people try to minimize it. Alright, so that was about marine corrosion. All the types of corrosion can take place under the marine atmosphere, but the cathodic reaction is controlled to the one which is valid for neutral and alkaline solution. The additional corrosion I have discussed here is the fouling, which is very prevalent and which is a must for all the ships docking, that their hull portion has to be cleaned of these organisms at a periodic interval. Another interesting type of corrosion is the stray current corrosion. Very interesting. Sometimes you have stray currents. Suppose you have a power plant or you have some kind of cathodic protection. So the current can leak. And this current leaks in the areas where, for example, you have an underground pipe and you have some kind of a electricity system, and the soil has a wonderful conductivity because of the presence of water. So instead of current flowing back through the channel, they start to take a shorter route and they kind of get conducted through the soil faster way. And that leads to the corrosion of underground pipelines and the storage tanks, especially the ones which are not protected. Now, in the mechanism, they are not much affected by oxygen or other things, not too much. They are mostly affected by the stray current. So how does it work? I've tried to slightly rearrange these slides, what you will be seeing in your lecture notes, slightly different. But the information is still the same. Origin of stray currents: electric railways, CPS, electrical welding mechanisms or machines, grounded DC electric sources. So here's a new picture. I don't think it is with you in your lecture notes. Suppose you have an electrically driven rail which is taking the power from here. Now this electricity can leak off, and suppose there's an underground pipe here, then this currents can leak and enter the pipe. So the place where the currents are coming out is the anodic area, and where it is entering, it is the cathodic area. Remember, anode releases electron. Electron is nothing but current, and cathode is the one which receives electron. So the place where they enter, this area becomes cathodic, shown by the green arrow here. It travels to the pipeline and then come out after a short distance. Now, where the current is coming out now, that becomes anodic area. So this part of the pipe becomes anodic, and the corrosion takes place, and it's a localized corrosion because it is leaving at certain point and going back, and this becomes an anode here, and wherever it goes back, that becomes a cathode. So the stray current can create anodic and cathodic sites and lead to the corrosion. Now if you look at this picture, for example, which should be in your lecture notes, you see another system where you have an anode and cathode. You have an anode here, you have a cathode here, some kind of a power system. So what happens here is that, and here is a tank here, and it is all underground. Now the current takes more resistance to go from here to here, and it forms an easy path. So the current will leak from the anode here, enter the tank here. So this becomes cathode here. Then it leaves this tank from the other side, and wherever it leaves, it becomes an anode here now. So the corrosion will be on this part, and then again it enters the cathode. So the stray current, if the currents are leaking, if you are not controlling the stray currents, the place where they enter the structure becomes cathodic, the place where they leave the structure becomes anodic, and that anodic part corrodes. So prevention, you have to find the source of stray current and stop the leakage. And number two, you can also install cathodic protection system to overrule this stray currents. So there are two ways to attack it. And that is the end of all different types of corrosion so far. If you can understand these types of corrosion, I don't think there's anything left for you. Let's try to look at this case study. This happened in 2003. In Tampines area of Singapore, there was a playground, and in the playground there were lampposts, and one lamppost on one fine day it fell on a little child, and he had brain damage as a result of that, and he could not be saved, and he died 3 days later. So this lamppost was about 18 years old. It was at the lowest point of the ground, and it was a damp area. And it was also checked about 3 days before this accident took place, and the inspector says it's okay, nothing wrong with the lamp. And 3 days later it happened. Now this iron post was galvanized, and you know now what is galvanized, covered by a layer of zinc to protect against corrosion. And they found that the crack was about 3 centimeter below the ground, which led to the failure. So question is, from a corrosion perspective, what do you think how this failure took place of this lamp? 18 years old lamp, typical life of these lamps is between 12 to 20 years. So it has already lived through its minimum life of 12 years. So it was 18 years old. Then it was galvanized when it was put in, and you know that is to prevent the galvanic corrosion. And the crack was 3 centimeters below the ground. The area was damp. So what really happened? And it was inspected by the inspector in 3 days back, and he told it is okay at that time, and suddenly the failure took place. So people were questioning whether you should blame the inspector that he did not do his job properly, or you cannot blame the inspector. So can you think about this situation and see what led to the failure of this lamppost? And this thing triggered the island-wise inspection of the lamppost, and hundreds of them were later replaced. And the think tank also designed the new type of lamppost after that accident, so that all the new lampposts should follow certain criteria in terms of design, so that such kind of accident can be eliminated. So I give you about 5 minutes. So think about it, and this will also tell you that not every time a failure from the corrosion can be due to one type of corrosion. It can be from many types of corrosion. Where one corrosion can happen, it can lead to the second type of corrosion that can lead to the failure kind of situation. So from the corrosion perspective, can you just like discuss with your friends and colleagues, and we will try to address this thing at 6:40. All right, anyone can make a proposition what really happened? Who want to try? This thing? Anyone want to try here? Want to give it a try? This thing? Any volunteer? Oh? How about this thing, the biggest thing? You want to try? Go ahead. Exfoliation. How will you get the idea of exfoliation? Not really. Exfoliation corrosion has to take place in the humid environment, and you have a certain section which is humid actually. But notice that the news article said there was a crack 3 centimeters below the soil, and the failure was because of that. So you have to focus on that. Yeah? Microbiological corrosion. Microbiological corrosion, if it has to happen under the soil, it should be in the whole area. But this was a single crack. Good attempt means these are the possibilities, and unless you apply it, you don't know that where you are going wrong actually. So it's good to try. Anyone else want to try? This is the last case study of the types of corrosion. So it has to be a combination of a few types of corrosion here. Let's try to analyze this case. If you look at this picture here, you see that the news article says that this segment of the lamp post 3 centimeters above and 3 centimeters below the ground is known as the critical areas with respect to the corrosion. So let's try to address this statement. 3 centimeters above the ground. Why it is critical for corrosion? Remember, it's a play field, it's a damp area, and you can expect rains, and you can expect people playing in the playground, obviously. That is the purpose. So why the 3 centimeters from the ground, that means 0 to 3 centimeters, is a critical area? What kind of corrosion you can expect? From 0 to 3 centimeters above. No, there is no waterline here. And waterline corrosion does not happen above it. It happens below it. We are concentrating at this point of time above the ground. So what kind of corrosion you can expect in a play field, damp area, people playing, doing all kind of things here? Which one? Stress corrosion. But why in 0 to 3 centimeters above the ground? Yes, possibility is there. But why 0 to 3 centimeters? What's that? Where is the cyclic loading? Fatigue is cyclic loading. This is a constant load. You need millions of loading for the fatigue. And these are so big that you can't even shake it. In fact, when the inspector comes, first thing they do is to see if they can shake these poles. If they can shake it, that means it is getting damaged. That is one way to check whether the lampposts are dangerous or not. So obviously you can't. A simple person cannot shift a few tons of load which is fixed in the ground. So that's ruled out. Any other guess? Water body. You don't have water above the thing. You can have the evaporated water, but there's no pool of water which can go 3 centimeters. It's a very big area, 3 centimeter, if you assume a ground. The only evidence is that it's a damp area, but it does not say waterlogged area. So, yeah. Crevice corrosion, that's correct. When the people play, the mud can splat and make deposit on the lower portion of the pipe, which based on their observation is about 3 centimeters above the ground. Crevice corrosion. Under deposit corrosion, that's the likelihood. Now let's go 0 to minus 3 centimeters. Go under the ground now. They also say that it is also critical area for corrosion. Now what can happen? 0 to 3 centimeters below the ground. And remember, this crack was found 3 centimeters below the ground level. So what can lead to the corrosion below the ground now? As I say that if there are bacteria, it will attack uniformly in that area because they will be there. At certain depth. So in that depth, they will attack. If you go down, they may not survive. So, but at certain area, they will attack uniformly. So question is that, now 0 to minus 3 centimeters, what you can think of happening? 3 centimeters. What reminds you of 3 centimeters? From the lecture notes. Waterline corrosion. Difference in the oxygen concentration. Because it's a damp area, so your water level is there. A typical humidity level or presence of water is there. Only difference can be difference in the oxygen at the surface and below the surface. And when you go to the waterline corrosion, again remember the corrosion takes place just about an inch below the waterline. So that is how much difference an inch, which is 2.54 centimeter to be exact, can make a difference. So initially the lamppost is galvanized, covered by a few micron thick layer of zinc, supposed to live through at least the minimum life of 12 years, maybe more. So over the time, what will happen? When you have a steel post covered by a few micron thick layer of zinc, what will happen over 18 years time? Think about it. What will happen to zinc? Do zinc corrode? Ask yourself. Will it corrode? 80% humidity in Singapore? Yes or no? Even gold corrodes. Yeah? So slowly you will lose the zinc coating over the time through the process of uniform corrosion. Because steel is all hidden inside the zinc layer. Even if you lose some of the zinc layer over the time, over the years, some cracks may come or it can completely dissolve off. It will still keep protecting iron. Remember the concept that zinc has much more negative electrode potential when compared to iron. So it always becomes an anode. So as long as it is there, it will still save. But in certain areas like ground level where the humidity level is high and the wet conditions are prevalent, you have neutral solution, your cathodic reaction will keep going on at some or other location. You will keep losing zinc over certain point of time. And once the zinc is gone in certain areas, then what happens? Now, no one can protect iron now. If no one can protect iron now, then the waterline corrosion sets in, where the difference in the oxygen amount at the surface level and below the surface level make a oxygen concentration cell. Less oxygen becomes anodic, more oxygen becomes cathodic. So the damage start happening below the ground. Crack will form over the time, it will keep growing. But the system will not fail unless the crack has reached its critical length. So once the crack reaches a critical length, imbalance of the force takes place and your system, in this case lamppost, will come crashing down. So this is exactly what is the sequence of the event which happened. Okay. I don't have that sequence of the event here, but that is essentially what happened. So you have the uniform corrosion of zinc, step number 1. Number 2, the oxygen concentration cell sets in, and that leads to the initiation of the corrosion below it. Then the lamppost have certain kind of stress. So now you have the corrosion happening below the ground, action of stress, and third stage is a stress corrosion cracking, because wherever the stresses are there, you call that as a stress corrosion cracking. Now if you see this picture here, for example, you see here is a lamppost. If you follow the cursor here, and here is all the lights kind of thing, so it's not like very aligned, so you can have not a vertical load, but you will have an inclined load. So the crack under the application of the load, so it will not be compressive load, it will be some kind of shear load happening in there, and that lead to the ultimate failure. Any questions from this case? So this case illustrates that you have more than one type of corrosion at time that can lead to the failure. At time it can be the single type also. It's not like every time multiple type. Here one type of corrosion leads to other one leads to the other one, and you have the ultimate failure. Now for the people who have read today's Straight Times, section A, it says that somewhere in the Bankolin MRT station, which is being made now, there's a pipe busted and a lot of water start coming down like a rain, and it busted at the corner. So can you tell what would have happened if you had to relate it with corrosion? Same material pipe, you know that the pipe changes the direction depending on the geometry of the structure or the place, and a lot of leakage, and the corner of the pipe gave up. So what kind of type of corrosion you think would have happened there? Straight Times, section A, today's newspaper. Think about it. Liquid carrying pipe, water carrying pipe failed at the corner. This is the clue, is that it's a single type of corrosion, not one after other. Because that station, I think, is still being built. So what type of corrosion you think would have happened there? Raise your hands if you have an idea. whenever you have the pipes carrying liquids failing at the corner, impingement corrosion. Go back to your lecture notes and see impingement corrosion. Always fail at the elbow. And exactly that is why whenever you have elbow kind of situation, you put much stronger and thicker material everywhere. And here it was not there. So now they are looking for a stiffer material. What do they mean by stiffer? Because they are not material scientists. It's not stiffer actually. It's thicker material. Thicker and harder material. That is the right term. Alright? So you have to read your lecture notes and try to read it a few times so that this get imprinted. Because pipes, first thing it should come to your mind, pipe carrying liquid going there. What is the flow related corrosion you can expect? Cavitation? Not really. It's not very turbulent. Erosion? Not really. It's only water. Impingement? There are only three. So that's how you should narrow down depending on the situation and catch it. Here's a picture. Whenever you see the lamp post standing and some kind of soil coming out, you can see this kind of corrosion happening just below the ground level. Here they have digged some of the soil and you see that this area is corroding and slightly above it is corroding here. So that is, this used to be the pole behind the engineering canteen. Now it does not exist. It removed already. Alright, so that is all types of corrosion we have finished today. Now you take a break, we come back and we'll try to understand the corrosion prevention mechanism, some kind of prevention mechanism which you can apply to most of the types of corrosion. Alright, so let's start at 7:15 and we'll start with the new topic. Alright, we can start with the rest of the lecture today. Now I'm moving to a new theme now about the corrosion prevention. And you must be very clear that corrosion in most of the cases cannot be eliminated. You can only minimize it. You can only extend the life of your structure. But you cannot eliminate in most of the cases. So we have to look for the ways in which we can minimize the rate of corrosion. And for understanding that, let's try to understand once again what is corrosion. So the corrosion is essentially interaction of material, as you can see it here, with the environment. So the first question you should ask yourself is, can I change the material? You can change the material. So that is the first situation. Can you change the material which is more compatible with the environment? If that is not a solution, second question you should ask yourself, can I change the environment which is more compatible with the material I am using? Which is possible in both indoor locations and outdoor locations also. And I'll show you some examples. Now suppose you have a situation when you cannot even change the material or you cannot change the environment, then the next thing is use the fundamental concept of corrosion, interaction. Can you minimize that interaction by putting a coating? So now you are separating the two. If they don't interact, they don't corrode. Number fourth, can you combine your material that is corroding with a more reactive metal, same way as we combine zinc with iron through the process of galvanizing? So can we attach? At time, the underground pipelines, tanks, they are all protected by attaching themselves to a more reactive metal which serves as an anode, and the structure that you are preventing serves as cathode. So that is called as cathodic protection. Now if all these methods, for example, are not cost effective, then you should also think about, can I change my metal-based material to a non-metal-based material if the things are not cost-effective? It is also possible. I'll show you some examples. And finally, you can also design your material so that your end structure is less susceptible to corrosion. So I'll show you some design principles which lead to that kind of improvement in the resistance towards corrosion. So having understood this, we will address how we can change the environment in neutral solution, acid solution, and the gaseous environment. Because the neutral solution also covers alkaline solution, because the cathodic reaction is same. Now all these things, if you see that there's a word which is called as inhibitors, so you will learn what the inhibitors are and how they help in minimizing the corrosion. Then I'll show you some examples of how you can change the composition of the metal to make it suitable for different kind of environment. So typical example I'll take is for iron, because iron-based materials are most commonly used materials from the weight point of view. For separation, you can have two type of coatings, metallic coatings or the non-metallic coatings. So you'll see some examples of that. In the cathodic protection, where the structure that you're protecting is made cathode, there are two ways to do that. One is the impressed direct current method. Second is the sacrificial anode type. So you will understand what these kind of methods are. Anodic protection is very interesting, in which the material you want to save, you make it anode. But this method is applicable for certain materials that shows active-passive behavior. So we take them into the passive zone by applying certain voltage. So once they're in the passive zone, they don't corrode. It's called as anodic protection. Then you will use the use of non-metallic materials. So I'll show you some examples. And then what kind of principle we can use to improve the design of the material. Modification of the environment. So what we see here are the two factors. One is the temperature, and another is the velocity. So basically we know that Arrhenius law, the rate of reaction is an exponential function of temperature. So you can minimize the temperature and minimize the reaction. So by that you can minimize the corrosion also. You can also reduce the velocity of the system, and by doing that you can increase the rate of corrosion. For example, if you see this graph here, on the y-axis you have log of corrosion rate, and x-axis you have temperature. So if you increase the temperature, your corrosion is going up. And this is for stainless steel 32205, 32101. Now for the velocity also you have the same thing. I think I'll take 5 minutes break. Just give me 5 minutes. just talking too much. Anyway, I'll see if I can continue. Anyone has some lozenges or something? Lozenge. Let me see if I can continue or not. Actually, the throat is giving away. So anyway, we are talking of this graph here, and we have the log corrosion rate and the temperature here. And we discussed that the corrosion rate goes up with the temperature based on the Arrhenius law. And same thing we can see for the corrosion of steel in the water. Again, you have the temperature here and you have the corrosion rate here. And you see that with increase in the temperature, in the open system, the corrosion is going up and slowing down. And if you look at the chemical plant, corrosion under insulation, you can again see that the rate of corrosion is going straight up. And the third situation is in the open system where the oxygen is free to escape. So basically what we see here is that no matter what kind of system we have, as long as the temperature is going up, you can expect the corrosion to slightly inch up only. And here is the curve for effect of velocity. Again, the velocity is on the x-axis, corrosion rate on the y-axis, and you can see that with an increase in the velocity, your rate of the corrosion will either go the linear way or it can go to a certain extent and it can stabilize. It will depend actually on the type of material that you are using, and because what happens at time is that when the corrosion rate, when the velocity is going up, it's also giving you the supply of oxygen, especially true for the stainless steel. So in that case, the corrosion stabilizes. But in some cases, the corrosion increases because your protective layer cannot stick to the metal surface. And when that happens, your corrosion rate follows a linear trend. And that is what is shown in case of B here for cast iron, which does not have a protective layer. So in the neutral solution, what happens is we have two ways in which you can minimize corrosion. And first is the de-aeration. De-aeration means, D means removal, aeration means air. So you can remove the air, and when you have removed the air, you are cutting down on the oxygen supply, and once you cut down the oxygen supply, your cathodic reaction cannot take place, your anodic reaction cannot take place, and the corrosion will proceed. And this is exactly the example which I illustrated with you about the ship trawler which came to Singapore water, and when these people went to inspect the trawler room, that chain locker room, there was lack of oxygen and no corrosion or very minimal corrosion. So that is the concept of deaeration. So this is very unique because you are not making any protective layer, you are only inhibiting the cathodic reaction, and that's how you control the rate of corrosion. Other way to minimize this corrosion, irrespective of the fact whether it's a neutral solution, acidic solution or basic solution, is by the use of inhibitors. And in the inhibitors, there are some kind of substances that you add in the system, and when you add into the system, then they come and make a protective layer on the top of the surface of the structure that you're trying to protect. So they can be two types. If they make a coating on anode, then they are called as anodic inhibitor. Stifles means slow down. So once they make a coating, they will slow down the anodic reaction. Similarly, if these inhibitors are like that they make a coating on cathode, then they minimize the cathodic reaction. Once the cathodic reaction is minimized or completely eliminated, again you will reduce the rate of corrosion. So let's try to have a look at anodic inhibitor. So they make the protective films on anode. So that is a basic mechanism. Now you see some kind of examples here. These examples are like hydroxide, silicate, borate, phosphate, benzoates on steel in the presence of dissolved oxygen. So the inhibitors are not like you use it for any kind of material in any kind of environment. You have to know your material and you have to know the environmental condition, and you can choose accordingly. So it's not like one shoe size fits all. It's not like that. Similarly, you use chromates and nitride in the absence of oxygen. So the message is, first thing, you don't have to remember the name of these inhibitors. Number two, that inhibitors are very specific in action for a given material and a given environment. So that's how it works. So lesson, choice of inhibitor depends on the type of material and environment. So once you know that, and you want to buy an inhibitor from the market, then you have to call the manufacturer. You have to tell that I have this material, I have this environment, can I or can you propose some inhibitor which will work under these conditions? Then you are on the spot. Now what you see here is that the inhibitor works by making a coating on the structure that you want to protect. Anodic inhibitor makes a coating on anode. As long as the coating is there is no corrosion. Absolutely minimal or no corrosion. They are very effective. They mask the whole surface of anode. This is a hypothetical system, corrosion system, in which you have anode and you have a cathode. Now you use anodic inhibitor. Human error, you don't add the specific amount. So once you don't add a specific amount, that means the part of the anode will not be covered. If the part of the anode is not covered, then your corrosion will be very intense. Do you know why the corrosion will be very intense? If part of the anode is not covered, as shown in the circle here, why the corrosion will be very intense? Recall the concept of galvanic corrosion. what was one of the very important lesson from galvanic corrosion? The size of the anode and size of the cathode. Remember that? The example of the shipping industry, the steel bolt in the copper sheet is a bad news. In the windows, the steel rivet, the aluminum rivet in the steel frame is a bad news. Same thing is happening here. Small anode, big cathode. So no matter how fast your anode want to dissolve, it will always be supported by the cathodic reaction and it will dissolve very fast. So that is why the attack will be very intense. So anodic inhibitors are good, but ensure there is no human error. Ensure you have done your calculation very well so that you can add the right amount of anodic inhibitor in the solution. So that is what we have to be careful about. Now let's go to the cathodic inhibitors. Same, they go and make some kind of a layer on cathode, and once they make a layer on the cathode, depending on whether your system is acidic or alkaline, now these ions will get, or it will be very hard for them, even if this masking is not very good, even if there are some holes, but most of the area is still covered. So since the cathodic area, in case of imperfect inhibitor amount, will still be less, and there will be still lot of resistance for the ions to go to the cathode and get reduced, whether it's hydrogen ions or hydroxyl ions or the oxygen. So once it happens, so once again, the examples are salts of such and such for steels in the aqueous environment. So again, the material and the environment is very specific here. Also, in case of steel, for example, at times the people add lime to the water, which helps in the formation of deposit, because if you look at the Porbig's diagram, the water is at 7 pH. And if you add the lime, it increases the pH. So now you are about 10. But when you shift from here to here, you are going from the corrosion zone to the passivity zone. Passivity zone means formation of oxide layer. And once you reduce the cathodic area, corrosion goes down. So here is the situation. If you use the same way, less amount of cathodic inhibitor as a result of human error, then you will have a situation that your cathode is not fully covered by inhibitor, masking is not complete, and you will have an area where the covering is not there. So will it increase the rate of corrosion? You made the same human error. Now part of the cathodic area is exposed, but say 90% is still covered by the inhibitor. So will the rate of corrosion increase or not? Yes or no? Anyone? It will not increase, because remember, any wet corrosion, the overall rate of corrosion is governed by the magnitude of cathodic reaction. Now, by masking 90% of the area hypothetically, you are reducing the 90% of the cathodic area. So now you have very small cathodic area. Same thing as shipping industry, ship made of steel, but the rivets are made of copper. Copper is cathode, steel is anode. Cathodic reactions are limited, so anodic reaction will automatically get limited. Is it clear to everyone? So the rate of wet corrosion is always controlled by the cathodic reaction. So if you recall, I also gave you an example. If you have to combine the two metals, the size of the anode should be bigger. That means the more active metal should be bigger, and the more noble metal, the area should be less, because you are controlling the cathodic reaction. Any questions? Because this is a very important concept which you must understand, that any wet corrosion, the magnitude of corrosion is proportional to the magnitude of cathodic reaction. Alright? Question here. What kind of polarization is triggered by using anodic or cathodic inhibitor? Remember, polarization is the slowing down of the reaction. Whether you mask anode or whether you mask cathode, you are slowing down either anodic or cathodic reaction respectively. So what kind of polarization? Activation, concentration, or resistance polarization gets activated? Do you remember? Activation polarization, because now you are controlling the interface of your electrode, which is either anode or cathode. That means the metal which is corroding is an anode. You are putting some kind of protective coating, so you are controlling the interfacial reaction. And slowing down of a corrosion as a result of the interfacial reaction is activation polarization. Alright? Same way, if you paint a material, you are activating activation polarization. But in the case of liquid batteries, where you have solution, after some time the concentration polarization kicks in, because now the diffusion of the ions from that solution takes more time to reach the cathode. Alright? So anything that you are doing with the interface is always activation polarization. Acid solution. You use acid solution in many engineering applications, and the common solution is use of inhibitors. So what happens? Iron-based material, when you process them at 800 degrees centigrade, they come out rusted, brown color rust. So you cannot use them in engineering application with that brown look. So they are passed through a solution, acidic solution, which dissolves the rust away and gives or restores the shiny surface. But if you are exposing your material to acid, it can also corrode. Your only purpose is to ensure the rust is gone, but the metal is not affected. So they use the inhibitors like pyridine thiourea, which gives a cover to the metallic area and expose the rusted area. In crude oil and petroleum processing, you have calcareous scales, calcium containing scales which are deposited, and they are not good because they can lead to the crevice corrosion. You have to remove them, and the way to remove is by using hydrochloric acid. But again, you don't want these acids to attack your metal surface, so you use the inhibitors like mercaptanes and glycol xanthates as inhibitors to take care of that. Nuclear reactors, radioactive isotopes are being taken care of by oxalic acid and orthophosphoric acids. And to mitigate that effect on metallic surface, again you use amines and derivative of thiourea. So once again, that only shows the application of the acid solution in some of the industries. You're not supposed to memorize the name of this inhibitor. It is only for your information. Mechanism is same. These substances you are introduced in the solution and they mask the area which you want to protect. If they are anodic inhibitor, they go to the anodic sites. If they are cathodic inhibitor, they go to the cathodic sites, mask it and minimize the corrosion. So that's how the inhibitor works. Let's try to have a look at the gaseous environment now. Very important. So in the gaseous environment, there are three factors: humidity, contaminants like sulfur dioxide, and dust particles. If these three elements are there, then they can react with the metals, even ceramics, and they can make some kind of oxide layers or sulfide layers, depending on what kind of gaseous environment it is. And they can even change the surface chemical composition, because once they react, if sulfur reacts with iron, it makes iron sulfide, so composition is automatically changed. If it is only oxygen and water, then of course iron hydroxide will form. So what we can do? Dry the air. We can do that in the air conditioned room by taking it less than 40% humidity. So we can in a way drying the air to minimize the corrosion. We can cut down the sulfur dioxide gas in the atmosphere. I'll show you the examples, what the governments of different countries are doing to minimize sulfur dioxide emission. Cut down the particle count, both outside and inside. And if you think of the microelectronic industry where the electrical circuits, the channels are only few micron apart, you cannot afford the dust particles in the manufacturing room. So whenever you go to see the pictures of people working in the microelectronic industry, you see they are all covered from tip to toe. Goggles and mask and the gloves and everything. Why? And the dust particle count has to be less than certain minimum level. Very high requirement, stringent requirement. Because the size of the dust particle range from about a few micron, like about 5 micron to about 20 microns. And the distance between this channel is less than that, less than 15 micron. So if you have a dust particles in the atmosphere, they can sit on two channels, short circuit that circuit, and the system fails. Now why the people ears are covered and the mask is there? Because if you sneeze, if you sweat, that serves as an electrolyte. Your sweat is a wonderful electrolyte. And it can lead to the galvanic corrosion, wet corrosion. That's why all parts of your body has to be covered. So particle count is important. Use of solid inhibitors. Now what happens? Singapore is pretty good because you don't see the power cuts here. Suppose you have millions of dollars of equipment in your system, which is very common with all the multinational manufacturing companies, and you are controlling the temperature, you are controlling the humidity, and one fine night electricity went off, everything shuts off. So immediately you are putting all this equipment at a high risk level of degradation. So under that situation, people use the solid inhibitors. So the very minute the humidity level changes beyond certain level, these inhibitors start evaporating and form a mask on this equipment, just protecting them from the corrosion. Now I'll give you one example. There's one company in Singapore, automotive industry, I will not take the name. They decided to cut down on the power bills. So they had all this manufacturing line and everything. Weekend they used to be off. And they thought, let's save some electricity bills, switch off the power on Friday night when the production is done for the week. And Saturday, Sunday, 2 days electricity off, we save a lot of bill actually. 2 days out of 7 days, right? 25% roughly saving. So they start doing that. Now, what they did not realize is when the aircon system are switched off for a longer time, then the humidity starts to come in and water start to condense on these different joints of the machine, and they start seeing the corrosion at the joints wherever the two metals are combining, wherever there are places where the water can accumulate. So the corrosion started. So within a few months they realized it is not the right thing to do, and they started putting this aircon on for the whole week, including the weekend. So wherever you, now that kind of awareness, I'm talking about 5 years back only, not long time back. So people are still learning. So, and the people who know that this kind of things can happen, use the solid inhibitors. So even if it goes in the night or something happens, the system is protected. That's where the solid state inhibitors are important. Let's talk about Singapore. Singapore is one of the highest emitter of carbon dioxide because it's quite a big center of the petrochemical industry. So that's one of the reasons. And of course, marine bunkers are there. So essentially about 40 tons per person per year, while the world average is about 4 tons per person per year. So essentially this was in news in 1998, and the government indicated that, okay, we understand it, but you have to understand that we are an industrialized economy, we are also a petrochemical center, we do that. So it is not because the people are using it, it's because the kind of industry we have in the thing, but government realized, appreciated, and they say that we'll start taking the steps by using the cleaner fuels, raising the pollution control standards, and giving the tax incentive to the companies so that they can minimize this carbon dioxide emission. Now let's try to look in 2006, 8 years later. From about 40 tons, it is 31.41 tons reduced, government action. And there are two ways in which the people say the carbon dioxide emission per capita is by the Energy Information Administration and International Energy Agency. And they say that EIA, which is very high, 31.41, includes the marine bunkers, while International Energy Agency 9.62, they don't take into account the marine bunkers. So 9.62 is a good figure, considering the average of the world is about 4 to 4.3 tons per person per year. So government involvement is very important. So why the carbon dioxide is very important? All the climatic changes that you see, forest fires in Alberta in January, coldest month, sub-zero, think about it. 3 months of rain in Chennai, India, in 3 days. So you can think of how much water would have poured down, created, the whole city was flooded, billions of dollars were lost. If you talk of Canada, a lot of natural resources were lost, a lot of life were lost. So all these things was happening because there's too much carbon dioxide being emitted by different countries of the world. So when this carbon dioxide, it can lead to the global warming, which I'm going to address a bit later. It can also react with the moisture in the atmosphere, upper part of the atmosphere, and lead to the formation of acid, carbonic acid, typical 5.6. If you burn the fossil fuel, you emit sulfur dioxide, sulfuric acid, and that leads to the acid rain. You also are emitting nitrogen oxide because of the industrial activities. And at times people felt that the volcanoes eruption and the forest fire also can acidify the environment, but later on they realized by research that whenever you have the forest fire, for example, or biomass burning that you see in Indonesia, for example, many times, you have the neutralizing ions which are also released. So they don't contribute too much to the acidification of the rainwater. But NOx, SO2 are the main contributors, and also some of the acids which are also being generated because of the industrial activities. Now in the Southeast Asia, where Singapore, Indonesia, Philippines, Thailand, Vietnam, Cambodia and Laos, you don't have a systematic recording of how much is the pH of the rainwater is. But in East Asia, which includes India, Bangladesh, Sri Lanka, Pakistan, the pH are typically less than 5.0, reasonably acidic. And in 2002, I got this data from a research publication. If you look at in Singapore, the pH is also less than 5, about 4.20. So that is an indicator of the industrial activity, emission of CO2 and SO2 in the atmosphere. Now this acid or rainwater, it can do a lot of damages. It can also affect the historical monuments worldwide, including the Taj Mahal in India. And they are trying to see that how these historical monuments can be prevented from this acidic rain. In China, for example, they use a lot of power plants. Again, in the most of the power plants, you use the fossil fuel. And this news came in 2007 because they realized that 1/3 of China is having acid rain. So again, the main source is the coal-fired power generators for the power plants. So the government also understand that, and they give the tax incentives and desulfurization facility for the fuel to minimize this sulfur dioxide emission into the atmosphere. So the smog can be as bad in many cities of the world where you cannot even see through and you have to use mask. Now we go to Bulgaria, for example. Again, the problem is same, and this problem was same 100 years back in what are now the advanced countries in Europe and North America, because the coal was used. So for Bulgaria, for example, to become a member of European Union, they have to maintain the environmental standard. Otherwise, they cannot join them. So how important it is to control the environment, and they know that it is coming from the use of the fossil fuel, and they also understand that SO2 creates acid rain. It can harm the vegetation, it can damage buildings, and it can acidify the surface water or the water bodies. So they are the three main damages, no matter where you are in the world. In fact, when I was in Canada, working with a company, nickel producing company, so they were also using the fossil fuels for their manufacturing. So I was new there, and I was advised by the people in the company, whenever there's a raining or the first snow coming in, don't step outside. If you have to step outside, take an umbrella with you. The reason, even if the snowflakes are coming because of solidification of the moisture, that area has a lot of sulfur dioxide, and if they hit your skin, you will feel itching in that, because it's all acidic in nature. So that's the kind of things which are still happening, especially in the industrial area. So essentially, they promise that we will cut down the SO2 emission by about 95%. So they will use filter to cut the dust emission, so that the industry like microelectronic industry is no problem. And what dust can do to human beings? It can cause the respiratory diseases, asthma. So you have to control the environment by controlling the
number of dust particles in the environment. And once they meet this certain criteria, then only they can become the member of European Union. So this news I picked up in 2007. I don't know whether they are member of European Union now or not. I've not checked on that, but that was conditions put at that time. All right. So what happens if you don't control the acid rain? Then, of course, when they are coming down, they're acidic, 4.2, and all these things. So they can affect the vegetation. They can affect the people who are exposed to the rain, animals, and everything. But if you don't control them, they can change the pH of the surface water. That means the water bodies like ponds, lakes, rivers, and all these things. And if that happens, that is very dangerous. Because if the surface pH is 6, you can see the death of snails and crustaceans. 5.5, the bigger animals and stronger animals, salmon, rainbow trout, and whitefish. If it reaches 5, perch and pike, 4.5, eels and brook trouts will die. So it has an effect. So that is why controlling the rain pH is also very important. And what you have to do is to control the sulfur dioxide emission. To control the sulfur dioxide emission, you have to control the fossil fuel. Now, fossil fuel is still the cheapest way to do that. But when the gases are emitted, you ensure that you desulfurize them, take care of sulfur dioxide somehow, so that it's not emitted. And once it is not emitted, then you have solved the problem already. Dust particles, put the filters, it will take care of it. So, but many people, many industries in many countries, they don't take care of it. So that is where the education comes in hand. So if you educate these people, it will be good for the health of the people. Acid rain, March 2013, backside of the School of Design and Environment on that road, Clementi Road, and you had a big hole appeared. And this kind of hole appeared a few times in Singapore. What really happened here? Acid rain, right? It can dissolve some of the soluble substances in the soil. Over the time, it keeps dissolving, and you have a road, and your underside the road, your soil is being dissolved, and the soluble components have been dissolved by the acidic rainwater. And one day, it caves in. So apparently, fortunately, no one died, no one went into that. So you can see many of the cars just squeezed just at the beginning of that and all this thing. And apparently it was filled up. And the size of the hole, 2 meter wide and 3 meter deep. Quite a big hole. So now carbon dioxide. It's very good for you to know what carbon dioxide can do. It's a greenhouse gas. What is the greenhouse effect? When you emit too much carbon dioxide, because you are burning carbon, you are burning coal, you are burning petroleum, all carbon-based products, right? CO2 is a natural outcome of that. So once you have the CO2, for example, going in the atmosphere, it leads to global warming. How does it work? It creates a blanket, a lot of carbon dioxide in there. So what happens is when you have the sunlight, then sunlight have very short waves. The wavelength is small. When I say short wave, means the wavelength is small of the sunlight. So when you have the small wavelength, it can penetrate faster. So it has much more penetrating power. Now it comes and get absorbed by the earth surface. So when it get reflected, now you have the longer wavelength. And when you have the longer wavelength, it cannot escape. So that means your heat is trapped between the surface and this gas layer. And that's what leads to the global warming. Alright? So basically, beside carbon dioxide, which is the main culprit, which does not allow this large wavelength rays emitted from the surface of the earth to escape, leading to the global warming, methane, nitrous oxide, CFCs, and ozones are the other gases which also contribute to that. Now based on this principle, Can you tell that when you park your car outside for a few hours and when you open the door, you find the inside of the car is very hot? Right? Have you experienced that? Why? If the outside temperature is say 25 degrees centigrade, the inside temperature can be easily 30 degrees centigrade. Why the car becomes hot from inside? Same concept. Try to understand why it becomes hot. Think about it. If you park the car outside and you open the door after 1 or 2 hours time, even 1 or 2 hours time, you will find it hotter from inside than the exact temperature of the outside. Anyone can answer? It's the same concept of the global warming. The sun rays have shorter wavelength. They can penetrate through the glass walls or through the window shields or the front shield. It can penetrate through. Then they get absorbed by the seats and other materials which are not perfectly black body. So when the rays are emitted back, they have a larger wavelength. They cannot penetrate outside. They get trapped inside. So the heat is generated inside, which cannot escape, and you find your car to be hotter. And exactly the same thing happens in the greenhouse gas effect, what we experience on Earth. All right? So I hope you have a clear idea. So you can, we don't have any artificial way to control it, except that people have found that sulfate aerosol, which can be there in the atmosphere due to the eruption of volcanoes, can scatter the light or scatter the rays. So what happens is that there's a particulate matter now, wherever these eruptions are. So when the sunlight comes in, it is reflected back from these particles. So they never come in really. They're reflected back right from the top. So there is no global warming. But of course, it does not happen. So the only way is that you control the use of the fossil fuels and control the emission of these gases. And use the cleaner fuels. Cleaner fuels from the wind turbines, from the hydroelectric dams. People are also generating electricity from the sea waves and all these things. So that's the only way to attack this problem. And of course, the nuclear energy, but that's controversial. Solar energy, people are trying to make advances, so that's the way to reduce this global warming. Scientists are even trying to see that whether they can use the bacteria to fight the contamination and also the corrosion which comes from the contamination. And they found that because of the industrial activity, there are a lot of halogenated compounds which are released to the environment, and they can be toxic and they can be cancerous. And of course, once they are contaminated, they can also affect the rate of corrosion of the material. So they found a unique group of bacteria which are called as dihacococcoids, who are capable of turning this harmful substance into non-toxic substances. And they can convert all these things into non-toxic things. And so bioremediation, that means they repair or they remove the contamination from the surface water, groundwater, soil and sediments. So this is some kind of new ways people are finding to fight these contaminants which are released to the industrial activities. So you have to keep your eyes open. At time, I was just talking in the break with some people that we have to keep updated with the coming technology, and some of this technology can be used. Very unusual use of bacteria. We know the bacteria cause corrosion, but we can also use the bacteria to mitigate corrosion also. Now, if we cannot change the environment, then can we change the properties of the matter? It's possible. And that can happen, or you can see from this single slide here, that the steels are basically iron plus carbon. They are steels. And if you add chromium and nickel to that as an alloying addition, then you have a steel which can do very well in the fresh water, lakes, ponds, they are the freshwater bodies. If you add molybdenum, so chromium nickel, just add molybdenum also in that, then you have the steels which are best suited for marine condition if you have no choice. So marine condition means you have chlorides. If you have a structure that needs to be welded and you want to minimize the intergranular corrosion, then you can use the titanium and niobium as an alloying addition, and you have a steel which is very good for fighting intergranular corrosion or minimizing intergranular corrosion. If it's a dry atmospheric condition, typically less than 40% humidity, then you can alloy your steel with phosphorus and copper. And that way, you have a wonderful material for atmospheric corrosion. If you have acidic situation, then you alloy your steel with silicon. And if you have high temperature application, you allow your steel with aluminum. All these steels are available in the market. So if you know your environmental condition, you can choose the appropriate steel, and that will take care of the corrosion under that atmospheric condition. So this is just an example for iron-based materials. So you have different materials which are suitable for different atmospheric conditions available in the market. So only thing is that you have to be aware of that. You have to see that what are the best possible materials that you can use for the given environmental situation. So this is one example. You can also, beside the proper composition, which we have just discussed, you can also do the heat treatment. By doing the heat treatment, for example, you can remove stresses, and hence you can take care of stress corrosion cracking. You can change the microstructure. You can remove second phases or minimize them, and by that way you can reduce the galvanic corrosion and also the exfoliation corrosion. And so on and so forth. So composition and the heat treatment can also be used to minimize many different types of corrosion. Alright? So in this case, I've given the example of stress corrosion cracking, or SCC here, galvanic corrosion, because once you remove the second phase or minimize it, you are trying to minimize the number of galvanic cells in your microstructure, and you minimize that. And exfoliation corrosion, by removing again the second phase or making the grain structure round, you can always minimize the exfoliation corrosion. So there are some of the examples which you can follow. So, if that's not good enough, if changing the material, changing the environment is not good enough, so can we separate both of them? If two people are fighting, you want to reduce the fighting or eliminate the fighting, the people can separate these two guys so they don't fight with each other. Exactly the same situation with the material and the environment. So let them not interact, and that can be achieved by use of coating. And you can have two types of coating, metallic and non-metallic coatings. This picture shows that wherever the coating is, no problem, no corrosion. And wherever the coating is damaged, you have corrosion. and here is where the damage will continue to go on and it will damage the structure. Non-metallic coatings like polymer-based coatings, rubber coatings can be used by the people. So plastics and rubbers are mostly used. And before sometime the people put this coating, they also, especially in case of steels, sometimes they paint it red. That red is nothing but a alkaline paint. The concept is still the same. You create an alkaline situation on the surface of steel and take the pH to a high value so that it is in the passivity zone. So iron will have a tendency to make protective oxides on the surface. So that is the logic behind the alkaline paint before they put any polymeric coating. So it's a double protection in a way. Now these polymer-based coatings are used, for example, in the pipes that carries water to your home. And in Singapore, for example, of course there is a standard. They line this pipe by UPVC. UPVC stands for unplasticized polyvinyl chloride. So these kind of polymeric coatings are given to the surface of the steel pipes that carries water so that there is no corrosion. Now let's try to go a bit deeper into this standard to have a better understanding. They also give external zinc coating. So you see, double protection. They take the steel, they galvanize the steel, and then they give this polymeric coating. And for polymeric coating, they have to ensure it sticks well, adhesion test, pinhole test. Remember pinholes in the polymeric coatings? That pinhole has to be avoided. So they are also tested. It's a quality assurance. And also ensure that this pipe will not give any odor or smell, taste, color, or toxicity to the pipe. That means they should not react, at the end of the day, they should not react or deteriorate when they are in contact with water. No color change, no odor, no smell, nothing. And then only it's approved. And ensure that there is no growth of aquatic microorganisms. Should not support that. This is nothing but microbiological corrosion. So all these things have to be taken care of. So whether you are using the pipe for transporting water, or you are using the pipes to transport the oil, or you are using the pipes to transport the chemicals, any purpose, corrosion is always a big issue. When you have the pipes with the hot liquids, with the insulation, then corrosion under insulation, it's always a big issue. So you have to have a good understanding of corrosion and how to manage it. The idea is management. If you understand all these things, you can take a best possible step to minimize it. You cannot eliminate, but you can minimize it. Same thing for the pipe, cast iron pipe fittings. If you have a pipe like this and you have a special fitting here, which is thicker. For the steel you use cast iron pipe fitting. Reason? Impingement corrosion. You need much harder and stronger material because the turbulence is maximum in this area. So again, UPVC, you can use it. And here is a situation when you have this nuts and bolt structure and they immediately give a galvanic corrosion. Because they may be different type of material, that's why the corrosion is only in these bolts here. So that is where we have to be aware of what are the good coatings here. So people tried fluoro-Chioti coating, number 1, and you can see once this is put in here, there is no corrosion. And if you read these numbers here, ASTM, American Society of Testing of Material B117, that means once you put a coating, there are standards here, and you can use a standard to test the quality of the coating to ensure that they are the right coating for your kind of application. So you have to test it under certain environmental condition for certain number of hours and see whether you can see any kind of corrosion or not. Chemical coatings. The coatings, when you apply it, they establish a chemical bond with the matter. They are called as chemical coatings. That's why the term is chemical coatings. Anodic coating, for example. Remember the question in the quiz, what happens when you increase the thickness of the coating, whether the corrosion resistance will decrease or increase? Anodizing, if you recall the case studies at the end of the dry corrosion, I told you that most of these aluminum things are anodized. Coating thickness is increased because the distance that ions has to travel will be more, and that's why the coating resistance will increase. So essentially it's a very common thing. So for aluminum based material, because it's very coherent with base metal. You can also have the chromate coatings for magnesium alloys and zinc, because magnesium is reactive in the wet condition. So you can put the chromate coatings. Phosphate coatings on steel, it was commonly used in the aerospace sector, but now of course most of the steel is replaced by aluminum based material, but still used in the critical component. So once you put a coating, you have a structure here and you put a coating on here. Obviously now this environment has to put a lot of energy to go and react with your metal. So it slows down the electrochemical reaction. So your corrosion is also slowed down. Mechanical protection, they are very hard coatings. These chemical coatings are harder. So once they are hard, you cannot scratch them easily. You can of course scratch them if you take a very sharp diamond coated tool, of course you can scratch them, but normal condition you cannot scratch them. So once you cannot scratch them, you cannot damage it easily. If you cannot damage it easily, you are able to protect the surface better. So they give you a mechanical protection on the top of corrosion protection also. Then you have metallic coating. That means the coating which are of metallic in nature. They do the same thing. They separate the metal from the environment. So now the second feature is they can give a galvanic protection, like the zinc coating on steel. It's giving a galvanic protection besides separating. They can be put in various ways. You don't have to remember these ways, like electroplating, splaying, dipping. It is just for your information. But this is interesting. You know that in aerospace sector you have to use the high strength alloys. So many times high strength aluminum based alloys are used. But high strength means more number of second phases. More number of second phases means more corrosion in the wet condition. So people say that single phase, how I can do that? So they take this high strength aluminum sheet and aluminum foils and they sandwich them and roll them together. So L-clad means AL stands for aluminum. Clad means now this high strength alloy is cladded by single phase aluminum, no galvanic cells. So your corrosion resistance is better in the normal situation. So they are called as L-clad alloys, commonly used in the aerospace industry. So let's try to understand the concept behind these coatings which are more active than the base metal and which are nobler than the base metal. Example, zinc coating on steel and the tin coating again on steel. Okay? Here the situation. Situation A here and situation B here. My first question, you have a piece of steel and you cover it all throughout with zinc. Second sample of steel, you cover it all by tin. Zinc makes a good oxide, tin makes a good oxide also. Alright? So will they corrode? Assuming the zinc has a high resistance to corrosion and tin also has a high resistance to corrosion. So will iron corrode or will they corrode if the coating is good in both the cases? Yes or no? Tin forms a stable oxide layer. Also zinc forms a stable oxide layer, and their inherent reaction with the environment is very slow when compared to iron. So they are the two type of coatings which are used on iron. Zinc is more anodic and tin is cathodic. But the first situation is you cover your two steel sample of the same steel, one with zinc and one with tin. Which one you think will corrode more, or both of them will show the same rate of corrosion? Similar rate of corrosion. What will be your answer? Coating is intact. No part of iron is exposed to atmosphere. Only coating is exposed to atmosphere. Anyone? And assume that interaction of the zinc and tin with the environment is similar. Means same rate of resistance, same level of resistance. So what do you say? Will both of them corrode in the similar fashion or in a different fashion? Anyone? See, now the environment is seeing only the coating. They are not seeing iron, right? And I have already told you that they have a similar interaction rate with the environment. So both of them should be corroding in a similar fashion. Okay? Now let's move on to the second stage when you scratch the coating. You see a big scratch here. Here's the scratch here, and here's the scratch. This is the tin coating, and this is a zinc coating, and this is the more negative electrode potential of zinc, and this is relatively more positive electrode potential of tin. So in case A or case B, in case A, let's look at case A. What will happen if there is a scratch? Will iron corrode? Well, now the atmosphere can see iron and zinc separately. Will iron corrode or not? Have a look at the electrode potential. Can you answer? Zinc is more electronegative. That means it has more negative electrode potential, to be more precise, not electronegative, more negative electrode potential. Which one will corrode? Zinc or iron? Which one will form anode? Zinc or iron? Yeah? Zinc or iron? The more negative electrode potential makes what? Anode, right? So that's what we do galvanizing for. So your zinc will corrode. So even if the scratch even if the environment is able to see iron, iron will not corrode. Now let's go to the case number B here. You have tin, which is more positive electrode potential, and you have iron inside with more negative electrode potential comparatively. Which makes an anode? Iron or tin? Iron will make it. Will it corrode easily or badly? Yes, the anode corrodes, right? But will the iron corrode easily or badly? Yeah? Badly or easily? Badly. That's correct. Why? Small anode and a very big cathode. Alright? Your statue is a small area, so the area is small for the anode. So always the golden rule. Anode should never be small. Again, it goes back to that shipping industry. Steel rivets and copper sheet. Bad news. Again, it goes to the same window falling from the homes. Aluminum, small anode and a big cathode. Never combined. Same thing is here. Alright, let's try to see how people, so it's very good for you to understand that it's not like coatings are just used on the material. This is only for your information and a wider understanding of how people establish which coating to do actually. So they do the atmospheric corrosion rate, expose the material in the open atmospheric condition, and they, for example, they use the steel here, low alloy steel, here it is, because it's cheapest, easily available, deformable, reasonable strength. So you can use it. So they use aluminum paint, number 1, zinc paint, number 2, organic paint, and no coating, 4. So 4 type of situation, and they found that maximum corrosion rate is of course when you don't use a coating, and minimum corrosion rate comes when you use the aluminum paint. So that is how, and they checked it in oil and gas industry, and they found that aluminum paint was the best and polymeric paint under these conditions, oil and gas industry is the worst. Alright? Then they did one more study. Again, low alloy steel in seawater, exposed to 14 days, temperature is 20 to 25, so everything has to be recorded. And now they use again the organic paint without coating, electroless nickel plating, and with copper oxide nanoparticles. So nanocomposite coating they wanted to evaluate. And what did they find? That electronickel plated coating with nanoparticle is the best. So that exactly is my answer to the 2 students who came in the break, that what coating we have to use. So these are the new developments which keeps coming again and again, and apparently we have to keep our eyes open to see what is the new technology coming. So if you look at that, aluminum paint, which was the best in the previous case, was 1.4. This is 0.584, which is almost 1/3. So that means you can increase the life at least by 2 times by using this kind of coating. So we have to keep our eyes open that what is coming new in the world and how you can improvise or help your company making wiser decisions. Alright, so that's all for the day. We will start with the cathodic protection in the next lecture. Remember, I sent the email. We will be meeting only on 28th of March now, so you have a 2 weeks break. I have to make some overseas travel urgently for some administrative duties by NUS. So we'll meet on 28th. But at the same time, please try to see my recorded lecture. If you're not understanding some part, take this opportunity to strengthen your concept so far. Alright? What has been taught so far. So I'll see you on 28th of March. If you have any question, you can just feel free to come down.